We've learned Demarva's theorem. We understand that if we have cos theta plus I sine theta to the power n, that is equivalent to cos n theta plus I sine n theta. It shouldn't feel trivial for this to be the case. It's a very strange idea to be pulling the n inside so it becomes a factor of the angle, if you like, rather than a power. It should remind you a little bit of the power rules with logarithms, but that makes perfect sense if we remember where Demarva's theorem comes from. It's a direct consequence of Euler's relation. If we have e to the I theta instead of cos theta plus I sine theta, raising it to the power n is of course equivalent to e to the I n theta. But now we've got that, we can make use of that theorem to generate all kinds of interesting trigonometric identities. And we're going to begin with one that we already know. We can demonstrate the double angle formulae, but we're going to come at it from a different angle, and we're going to start from Demarva's theorem and derive the double angle formulae. And while I do this, I recommend you think carefully about the steps that I'm following so that you can have a go at following the same steps and see how well this process scales to things like triple angles. So let's begin. I'd like you to expand cos theta plus I sine theta squared so that you generate an expression involving sine theta, cos theta, maybe sine times cos or a sine squared, but nothing involving double angles yet. You're not going to assume the double angle formulae, you're just going to expand that out as a pair of double brackets. Okay, what you should have is something like this. We get cos times cos, we get I sine theta times I sine theta, so I squared sine squared theta, and then the middle terms are both cos theta times I sine theta. But of course we can simplify a bit, because anytime you see a power of I, you can reduce it down to either 1 or I, or minus 1 or minus I. So I squared becomes minus 1, and that allows us to group the real terms, the cos squared theta and the minus sine squared theta in one place, and the imaginary terms in another place. You can probably already recognize from writing it in this format where the double angles are going to come from. The next step in the process is to apply Demarva's theorem. This bit is quick and simple, it just uses a very powerful tool. So Demarva's theorem allows us to rewrite cos theta plus I sine theta squared. So do that, apply the rule in the blue box, and then unpause the video. What you should have now is cos 2 theta plus I sine 2 theta. And all that remains to do is to compare the real components of these two sections. There's the cos 2 theta, the real bit, and here's cos squared theta minus sine squared theta, the real bit up at the top there. And then the imaginary components, the sine 2 theta and the 2 sine theta cos theta. If we compare those two, that will give us our double angle formulae. So now we know that cos 2 theta is cos squared theta minus sine squared theta, and sine 2 theta is 2 sine theta cos theta. Most importantly, if you think about the process we've followed, and think about how well it will scale, what will happen when we change the squared to a cube or raise it to the power 4, think about the kind of differences we're going to get in each step. And if it feels like something you can do, then that demonstrates that this process we followed here, this relatively quick 3-4 line process, is sufficient to construct not just the double angle formulae, and it's 2 for the price of 1 because we've got cos 2 theta and sine 2 theta all in the same term, but also it should allow us relatively quickly to generate things like triple angles. That's what we're going to do next. So follow the same sorts of steps. Make sure you pause the video and work through this for yourselves. See if you can construct an expression for cos 3 theta and an expression for sine 3 theta by following these steps. When you're ready, unpause and we'll continue. So the first bit expands out like this. You'll notice I'm using the lazy version. If I want to talk about cos theta and sine theta a lot, then often it's tempting to use a simplified version. It's fairly standard practice to use C to represent cos theta and S to represent sine theta, and it certainly makes things a bit quicker here. Ideally, if you're doing this in an exam situation, you want to be explicit about exactly what you're doing. So you might write something like let C equal cos theta and S equal sine theta at the top. But once you've done that, it's fine to continue using this shorthand notation throughout the rest. one thing you want to be careful of is that if you're ever dealing with cos of 2 theta, that cannot be described with the same shorthand letter as you would have used for cos theta. So be a little bit careful with that. As long as you're consistent, this approach can save you quite a bit of time. Now, the next step here is to simplify things. And again, it's important to pick out carefully the real components and the imaginary components. So these two parts are real, and these two bits here are going to be imaginary. The way I can tell is that any even power of I will be either 1 or minus 1, whereas the odd powers of I will be either I or minus I. So where we have a term involving just I, it's obviously imaginary, 3 cos squared sine multiplied by I, and then anything involving I cubed is also imaginary, but I cubed is the same as I squared times I, so minus 1 times I, so minus I, and that's where the minus s cubed comes from. Once you've got that written out and you've got the real part and the imaginary part separate, then most of the hard work is done. The next part is Demarva's theorem, which is relatively quick and simple because we're just applying that general rule. And then the final step is to equate the real parts and equate the imaginary parts. So the real parts are cos 3 theta, but also cos cubed theta minus 3 cos theta sine squared theta. And the imaginary parts are the sine 3 theta bit from there and the 3 cos squared theta sine theta minus sine cubed theta. So we write them without the i's and we just get the triple angle formula for sine 3 theta. And even though we relied on complex numbers and some sophisticated techniques to generate these, they are just as valid and real for real numbers as they are for complex numbers. A couple of things you might want to think about at this point. You may even have written your formulae in a slightly different form. You might have jumped ahead and tried factorizing things. You might even have found a way of writing cos 3 theta in a way that involves cos 2 theta. Who knows? Perhaps one or other of them could be written exclusively in terms of either sine theta or just cos theta, in the same way that cos 2 theta can be written only in terms of cos theta if you want, or only in terms of sine theta. And if you're feeling like a challenge, then maybe take these two triple angle formulae and combine them to generate a triple angle formula for tan. And if you've managed that, then can you simplify it in such a way that your formula only involves powers of tan theta rather than sines and coses? I'll show you an example that does that later on, so if you're a bit stumped and you're not sure where to begin, don't panic, because there'll be something on that later. The next thing you can try is from the textbook, Core Pure 2, exercise 1D, just the first 3 parts of question 1 and question 2 for now. Should be enough to practice this particular technique. Okay, so now we're able to rewrite multiple angles, cos 3 theta and so on, sine 5 theta, etc., as powers of sine or cos theta. What about going the other way around? What if we want to be able to write powers of sine or cos in terms of multiple angles? One reason this might be useful is for integration. It's not easy to integrate sine to the power of 5 theta, but it is really straightforward to integrate things like cos 4 theta or sine 3 theta. Remember this? If you're trying to integrate cos squared theta, you might use a rearranged version of the cos double angle formula so that you can turn it into something that's easy to integrate. So imagine if you're trying to integrate something more complicated, it would be really handy to have that kind of formula. But it's not always going to be straightforward like it was for the double angle formula to rearrange the sorts of things that we're able to create, like the triple angle formula we just did. Sometimes it'll be useful to be able to work backwards completely. So we want to start with something like sine to the power 6 theta and have a quick, efficient way of converting it into sine or cos of 2 theta, 3 theta, 5 theta, whatever it might happen to be. To begin with, because this particular technique is a little more obtuse, I think it's harder to see where it's going. It's a harder thing to generate on your own unless you've spent a lot of time playing around with it. I've got a few questions for you to answer that may seem unrelated to begin with, just so we can start spotting some patterns. So we've got x plus 1 over x cubed and x minus 1 over x to the 6. Pause the video, have a go at those. When you're ready, unpause and we'll continue. So what I have here, if we expand this out, we can use a bit of binomial to help us. If it's a cubed bracket, we will need the binomial coefficients 1, 3, 3, 1. We'll also need decreasing powers of one of the nomials, one of the numbers in the bracket. So I've got x cubed, x squared, x and x to the 0 or 1, and then increasing powers of the other nomial. So 1 over x to the 0 is just 1 at the beginning, 1 over x to the 1, 1 over x squared, and 1 over x cubed. But what's interesting about this is that because the x terms and the 1 over x terms can combine and cancel out, we get quite a nice pattern. And if you simplify enough, you can rearrange it into this form. You may not have had it written exactly like this, that's fine, but it's worth noticing that because of the structures and the symmetry involved, this is always going to be the case, even for bigger, more complicated expansions like the second one. It should be possible to pull out related terms, I suppose, reciprocal terms, x cubed and 1 over x cubed added together, x and 1 over x added together, and we just have exactly 3 of each of those, 3 x's and 3 1 over x terms, because of the symmetry of the original binomial expansion. If you've done the second one, this is the first thing that you might have got. It's a bit of a mouthful, so I'm not going to read it all out, but hopefully you can see the structure and the pattern within it, and you'll find that if you do a few of these, you'll get quite quick at combining them. You'll be able to incorporate the binomial coefficients, the increasing powers of one of the nomials, the decreasing powers of the other one relatively efficiently. You just have to be a little bit careful if there are negatives involved, because whenever you have an odd number of minus 1 over x terms multiplied together, you'll get a negative term, and whenever it's an even number of them, they'll cancel out the minus sign, so you'll get a positive term. But this also simplifies in a similar way. We get an x plus 1 we get x to the 6 plus 1 over x to the 6. We get an x to the 4 plus 1 over x to the 4. There's actually minus 6 of those altogether. And we'll get 15 lots of x squared plus 1 over x squared. So even though there were lots of minus signs around, the symmetry of this one meant that we still ended up with the sum of 2 reciprocal terms. That's not always going to be the case. In some situations, you'll find you get things like x to the 4 minus 1 over x to the 4 in that bracket. But as we're going to see in a minute, that's not really a problem. You'll see when I start demonstrating what we're going to use these results for. The next thing I want to look at is this particular sort of corollary, I suppose, of Demarva's theorem. If you have a power of minus 1, you can bring that power inside your trig functions. So cos of theta becomes cos of minus 1 theta. Sine of theta becomes sine of minus 1 theta. But cos of minus theta is the same as cos theta. Sine of minus theta is equal to minus sine of theta. So it can be quite helpful to think of 1 over cos theta plus I sine theta as just being cos theta minus I sine theta. And if we do that, then it turns out, as you might remember from an earlier video, we can combine things quite nicely. So start with z equals cos theta plus I sine theta, so some complex number with a modulus of 1 somewhere on that unit circle, but with any argument you like, theta, and see if you can write it in terms of sine theta and cos theta, the following things: z plus 1 over z, z minus 1 over z, z squared plus 1 over z squared, and z cubed minus 1 over z cubed. Pause the video and calculate the values of each of those expressions. See if you can simplify a bit and see what you notice. When you're ready, we'll continue. This first one, z is obviously cos theta plus I sine theta. We've mentioned above that z to the minus 1, in other words 1 over z, is cos theta minus I sine theta. So it turns out 2 of those pieces cancel out. The I sine theta and the minus I sine theta disappear, and we're left with just the real components. We end up with 2 cos theta. A similar thing happens if you subtract those terms, but in this case, it's the cos thetas that cancel out. and we're left with 2 times I times sine theta. Remember that I. Don't forget the 2's, but also don't forget that when it's the sine theta term, there's an I in front as well. Even more interestingly, when we deal with z squared and 1 over z squared, we find similar cancellation happens. So we can use Demarva's theorem to turn cos theta plus I sine theta squared into cos 2 theta plus I sine 2 theta. So that allows us to simplify this whole process quite a lot. Similarly, cos theta plus I sine theta to the minus 2, well, you can bring that minus 2 inside, but it does the same kind of thing as bringing a minus 1 inside. Cos of minus 2 theta is just cos 2 theta, and sine of minus 2 theta is minus sine of 2 theta. And once you've done that, you have another look, and you'll find that things cancel out. In this case, we're cancelling the I sine 2 theta terms, and we're left with 2 lots of cos 2 theta. And a similar thing happens with the last one. And again, it's not much more work to demonstrate it. In fact, because it doesn't require a binomial expansion or anything like this, you could even prove the results generally just by putting an n in there. Z to the n plus 1 over z to the n, z to the n minus 1 over z to the n. So we generate a set of useful results that are worth committing to memory, and you'll be using these to do the thing that we're trying to do, write powers of sine or cos in terms of multiple angles. So the first one is this. The sum of the complex number and its reciprocal is 2 cos theta. The difference is 2I sine theta. If you then incorporate a power on both terms, so z to the n and 1 over z to the n, they add together to give 2 cos n theta. So the only difference is that the power has been incorporated as a coefficient in front of theta, just like in Demarva's theorem. And then the corresponding result for sine theta, we get 2I sine n theta when you have z to the n minus 1 over z to the n. You might already be recognizing the structure that we're dealing with here and thinking about how it's going to combine nicely with what we noticed on the previous slide. We started out by expanding using binomial things like z plus 1 over z to the power 3 or x minus 1 over x to the power 6, and the result was terms that looked a lot like questions 3 and 4 on this slide. Maybe z to the power of 4 plus 1 over z to the power of 4. So they kind of link up. That's what we're going to look at next. We're going to investigate how we can combine those two ideas. So we start with z, cos theta plus I sine theta. And we're going to make use of this result first. We're interested in this case in finding a way of representing cos cubed theta that only involves single powers of multiple angles. So I'm happy with a cos 2 theta or a sine 3 theta. Things like that would be fine. And I can have as many of those as I need, but I just want to get rid of the powers involved. Well, I know that z plus 1 over z is 2 cos theta. So maybe I start with that, and I say to myself, I need cos cubed theta, so I'm going to cube both sides. And if I do that, then obviously the right-hand side is very quick and simple to evaluate. 2 cos theta cubed will give me 8 cos cubed theta, which means all I need to do to find an expression for cos cubed theta is to expand this and then divide it by 8. So let's try it. We can expand z plus 1 over z cubed. You'll recognize this result from when we did it with x plus 1 over x cubed a couple of slides ago. What we end up with when we simplify things and group things conveniently is z cubed plus 1 over z cubed and 3 lots of z plus 1 over z. Well, we already know where the z plus 1 over z term is going to go because z plus 1 over z is 2 cos theta. But remember, z to the n plus 1 over z to the n is 2 cos n theta. So both of those terms can easily be converted into singular powers of cos. So there we are. We have 2 lots of cos 3 theta plus 3 lots of 2 cos theta. Then we go back. We remember that that expanded bracket is equivalent to 8 cos cubed theta, and we divide by 8, and we get cos cubed theta is equal to a quarter of cos 3 theta plus 3 cos theta. So there you go. You may not have been able to integrate cos cubed theta very easily before, but it's the work of a moment to integrate a quarter of cos 3 theta plus 3 cos theta, because each term is just a single power of cos or sine, and what's inside is just something linear, 3 theta. So it's nice and straightforward to work with. Remember, there's a couple of other results here. So if you try some examples and you end up with a z minus 1 over z, or a z squared minus 1 over z squared, you don't need to panic, you just need to use sine instead of cos. But don't forget, when it comes to sine rather than cos, we've got slightly different results. We have 2i sine theta and 2i sine n theta. So watch out for the i's. You could have a go at doing the same kind of thing for sine cubed theta. You'll need to start with z minus 1 over z and cube that, but the process should feel pretty similar. Once you group things, you look at these 4 results that we've got in the blue boxes, and you should be able to construct for yourself an expression for sine cubed theta. And if you're not sure if it's correct, well, you could just try some numbers in the right-hand side and the left-hand side of your identity to see if they match. It's not a proof, but it'll be reasonably convincing, and it's likely to demonstrate any discrepancies if you've made an error somewhere. The next thing you can try is the last couple of question parts from question 1 in exercise 1D. Those involve this particular technique. Now I want to try to talk about both methods, because even now, probably over a decade after I first came across these methods, I still get in a muddle sometimes about which method I'm supposed to be using when. Fortunately, if you're efficient enough, you can just start a method and then realize where it's going and switch across the other method if it's not working. But I think it's helpful to spell it out a bit more clearly and look carefully at the 2 different methods that we're applying. It is very easy to get mixed up. Essentially, they're both a consequence of Demarva's theorem in one way or another, and they're both methods for constructing trigonometric identities that connect multiple angle forms with powers of sine and cos. So in that sense, they have a lot in common. The process is a bit different, and they both take a little bit of time, so you don't really want to be fiddling around, faffing about with one format and generating something completely unhelpful when actually what you need is the other one. So if you've got powers of sine or cos, and you want to convert them into multiple angle forms like cos 4 theta, sine 8 theta, or you've got the multiple angle forms and you want to convert them into powers, you need to know which of these 2 methods you should be using. So if you're going from the multiple angles to the powers, we are thinking in terms of, I've got cos 4 theta perhaps, and I'd like to write it in terms of powers of sine and cos. Then the method is the first method we went through. You're going to expand cos theta plus I sine theta to the n using binomial expansion. Just expand out the brackets, and that will give you a bunch of powers of cos and sine. And then you're going to rewrite cos theta plus I sine theta all to the n using Demarva. That will give us the cos n theta and the I sine n theta. And that is how you link to the thing you started with. And you'll generate expressions for multiple angles that look like this. So cos 4 theta can be converted into some combination of powers of, in this case, we can write it just with cos thetas. You could, depending on the expression you get, you might find it simplest to write it with coses and sines. It might be that you're able to write it exclusively in terms of just one or just the other. But what matters is it's a method for taking a multiple angle term and rewriting it in terms of powers of sine and cos. Now, what if you want to go the other way? If you're trying to turn those powers of sine and cos into multiple angles, for that you need the other method. So you'll choose either z plus 1 over z or z minus 1 over z, depending on whether you're interested in sine or cos. And then you expand that thing to the power n, whatever n is, because that is going to allow you to generate a bunch of different terms which are all multiple angle terms. But when you refer back to your original term, if you've got something involving cos theta raised to the power of 7, then obviously that's going to give you some expression for cos to the 7 theta. So for instance, if you're using this method, you'd be able to convert cos to the 4 theta into something involving various multiple angle forms of the trig functions. If you're wondering about why we might do these, well, a couple of the most common applications that you'll come across at this point involve either connecting trig to polynomial equations, which is useful if you're trying to solve something, let's say this particular quartic equation, 8x to the 4 minus 8x squared plus 1 equals 0. Well, the structure of that lends itself nicely to a substitution. The roots of that equation are closely related to the roots of cos 4 theta equals 0. But of course, cos 4 theta equals 0 is a year 12 A-level maths type problem. That can be really quickly and easily solved. But using the solutions from that, you can generate solutions for the polynomial. And vice versa. If you've got a polynomial that you can solve directly in some other way, then you can use those results to give you exact values for various trig results. Now, on the other side, we've already briefly mentioned this. Why would you want multiple angles instead of powers? Well, integration is the big hitter here. Anytime you want to integrate something involving powers of sine or cos, being able to convert them into multiple angles is a really helpful way of turning your integral straight away into something which is basic. As long as you can integrate cos and sine, and you know how to deal with a function inside another function where the inner function is just linear, so pretty much basic integration with a bit of inspection, then this process makes your integral into something really quick and straightforward. Next, we're going to do a couple of examples for each of these, just so that you've seen it a few more places, and then you can have a go at a few more questions. So find the integral of sine cubed x. You're not told how in this particular question, so if you could come up with another method that worked, then by all means you could use that. But we're going to show how we can make use of this approach. Since we've got sine cubed and we would like it to be written in terms of multiple angles to make it easy to integrate, we're going to start by using this result, z minus 1 over z equals 2i sine theta. If we cube that, then we know we're getting 2i sine theta cubed, which turns into minus 8i sine cubed theta. All we need to do now is expand out this stuff and divide it by minus 8i, and we'll be left with sine cubed theta. So that's what we do. We expand out z minus 1 over z cubed. You'll notice this time, once we group things together, we get negative signs inside those brackets. That's why we have sine appearing instead of cos. So z cubed minus 1 over z cubed. We've got a z minus 1 over z term, and we can make use of the standard results there. So if it's the difference of z cubed and its reciprocal, we'll have 2i sine 3 theta. That's where this one goes. And then if you just have z minus 1 over z, that's the same as 2i sine theta. When we simplify that a little bit, we get a purely imaginary term, 2 sine 3 theta minus 6 sine theta I, which is reassuring because we're looking for some identity involving sine cubed x that doesn't have any imaginary components in it at the end. We're making use of the complex plane in order to construct the results, but then we're going to just pull out the bits we're interested in. So now we equate the two sides. We have minus 8i sine cubed theta, and that's equivalent to 2 sine 3 theta minus 6 sine theta I. So when we divide by minus 8i, the i's disappear. So they're going to cancel out. And we can divide by the minus 8. That's going to change the sign and cancel some things. We get 3 sine 3 theta minus sine theta. So I've used up most of the slide just converting sine 3 theta into something more usable, but fortunately, we've now done 80% of the work. The last thing to do is to integrate, and that's relatively straightforward. If we can make that conversion, then we can integrate. Sine 3x integrates to minus cos 3x over 3, so the 3 cancels out. And then sine x integrates to minus cos x, so we get a minus minus cos x, and that gives us a plus. This next example looks fiendish, but if we take a minute and look carefully at it, we'll be able to see some clues within it as to how we should proceed. On the left-hand side, we have a multiple angle term, tan 5 theta. And on the right-hand side, we've got something messy, admittedly, but it involves only powers of tan theta. Now, not getting hung up on the fact that it's tan at the moment, think about sine 5 theta or cos 5 theta. We can rewrite both of those in terms of powers of sine theta and cos theta. So presumably, if we could generate expressions for those, we could generate an expression for tan 5 theta, at least something that involves powers of sine theta and cos theta. Converting that into something that involves powers of tan theta is a bridge we'll cross when we come to it, but trust me, it'll work. Let's start with Demarva's theorem. That allows us to convert cos theta plus I sine theta to the 5 into cos 5 theta plus I sine 5 theta. And this is my first indication that I'm using a sensible method, because I've straight away got a cos 5 theta term, and I've even got a sine 5 theta term at the same time. So when I find a different way of expanding cos theta plus I sine theta to the 5, I can equate the real bits and I can equate the imaginary bits, and I will generate for myself the expressions I'm looking for. So now we expand that left-hand side using binomial, and you'll notice again I'm using the C to represent cos theta and S to represent sine theta shorthand. The coefficients are 1, 5, 10, 10, 5, 1. You can pull those off a quick scribble of Pascal's triangle, or you can generate them by using 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, 5 choose 5 on your calculator. Now we need to group them. So look carefully and you'll be able to identify the real bits. That one's real because there's no i's. This one's real because it's I squared, an even power of I. And this bit's real because it's I to the 4. The imaginary parts are going to be anything with an odd order for the I term. So I squared wouldn't work, but I cubed will. I4 no, but I5 yes. Once we take those and we sort them out, so I to the 4 will just disappear completely, but I squared will turn into -1, I cubed will turn into -I, and so on. We should be able to generate something like this. And I'm going to leave it in that form for the moment, and we're going to equate the real and imaginary parts. So cos 5 theta from the top line we wrote is equivalent to cos to the 5 minus 10 lots of cos cubed sine squared plus 5 cos sine to the 4. And we get a similar expression for sine to the 5. Now we need tan 5 theta. So we're going to use cos 5 theta and sine 5 theta and divide, and that will give us tan 5 theta. Then we're going to simplify, and the simplification step is really clever. So once we've done the division, we've just got a big messy fraction, and you could look through and you might be hoping there'd be a common factor. But as you hunt, you realize, well, there's a sine theta to the 5 on the top, and there's a cos theta to the 5 on the bottom. They don't share any common factors, those two terms. So even if you could factorize the top and the bottom, which is possible, you can pull out various things, you can't fully simplify just by taking out common factors. We've got to do something a little bit cleverer. Fortunately, though, if you look closely, you'll realize every single term has got exactly 5 either sines or coses. We've either got 4 coses and a sine, or 2 coses and 3 sines, or 5 sines, or a cos and 4 sines, etc. And tan theta is equal to sine theta over cos theta. So the trick we're going to pull here is to divide through the top and the bottom of this fraction by cos to the 5. Now, that means that the cos to the 5 term on the bottom left is going to turn into 1. It'll essentially cancel out. But the sine to the 5 term on the top right is going to turn into sine to the 5 over cos to the 5, which is tan to the 5. Not only that, but in every single other term, you will either be cancelling out coses or you'll be turning sines into coses. And there's exactly the right number of each to make sure that in every single case, we have the same number of sines on the top of the fraction as we have coses on the bottom of the fraction. So it's very neat, very clever. And as you can see, it generates exactly what we were asked to prove at the very beginning. We've got 5 lots of tan theta minus 10 tan cubed plus tan to the 5 all over 1 minus 10 tan squared plus 5 tan to the 4. So there we go. We've got, albeit a messy one, we've got a formula for tan 5 theta. But the question's not quite over yet. The second part of the question that would generally come is something involving some messy polynomial. This particular polynomial is a quintic, so it's an order 5 polynomial, and as you might recall, the number of roots for an order 5 polynomial should be 5. They're not necessarily all going to be real roots, but there should be exactly 5 solutions. And generally speaking, it's not possible to directly solve equations of this type. There is no known method, not only no known method, but it's been proven that there can be no method, no formula for solving an order 5 polynomial. But this particular polynomial has got 5s and 10s and minus 5s and things that look a lot like the fraction above. And with a bit of work, we might be able to see more closely why it looks like that. In fact, our powers of x and the powers of tan theta are the things that you want to try to connect. It's got the word hence, so we know we need to be looking for a connection. And generally speaking, in this case, what we're going to be doing is some kind of substitution, replacing x with tan theta in this case. So if we put tan theta in instead of x, let's see what we get. I'm not going to write out tan theta every time, but we'll just use t to the 5, etc., etc. Well, that's no different to what we've written above, but we can start rearranging it a little bit. You'll notice if I pull a few terms across to the right-hand side, then what I've got on the left matches the numerator of the fraction at the top of the page. What I've got on the right matches the denominator. So what if I divide by the right-hand side? On the right-hand side, I'm dividing a thing by itself, so I get 1. On the left-hand side, I get a fraction, which is identical to the thing in my original expression. And the identity I had at the beginning allows me to rewrite that as tan 5 theta equals 1. That entire messy quintic equation is equivalent, in some sense, to the solutions to tan 5 theta equals 1. All we need to do is pull out some solutions. Now, as you know, there isn't just one solution for a trig equation. In fact, there are infinitely many solutions. If you've got one, chances are you've got as many as you might need. But it's not just that solutions for theta give us solutions for x. It's a bit more subtle than that. Even if there are infinitely many angles that work, there won't be infinitely many values of tan of those angles. You'll see as we go through. We'll start by finding the first few solutions for theta. And then from there, we're going to generate solutions for tan theta. So if tan 5 theta equals 1, that means 5 theta must be inverse tan of 1. Or the principal solution is just inverse tan of 1. And that's pi by 4. But we can generate more solutions by just adding multiples of pi. So I've started with that. Pi by 4, 5 pi by 4, 9 pi by 4, 13 pi by 4, 17 pi by 4. I've listed 5 of them, because I'm expecting 5 solutions for x. And then once I've got all the solutions for 5 theta that I think I need, then I'm going to divide everything by 5, and I get all the solutions for theta. Once I've got those, I turn them into solutions for x. And these are my answers. So the solutions to that polynomial are tan pi by 20, tan 5 pi by 20, and so on. And you can check, you can verify this with a calculator or with a spreadsheet to see that each of those gives a different number, but also you could check to see what happens if you go a bit further. If we take the next solution for 5 theta, it's going to be 17 pi by 4 plus another pi, so 21 pi by 4. Well, that will give us 21 pi by 20, which is exactly pi above pi by 20. And if you do tan of that value, you'll get the same answer as tan of pi by 20. So although you could argue there's an infinite number of solutions for 5 theta and therefore an infinite number of solutions for theta, once you apply tan to the infinite number of solutions, you find the same 5 solutions going round and round. Worth noticing, if you try sketching the graph, tan of those angles, although the angles are progressing in nice regular spaced jumps, tan of course doesn't progress in nice regular jumps. It's got its own weird and wonderful pattern. So this particular quintic equation is also a bit weird and wonderful, but you can check that those solutions do correspond to the points where the graph crosses the axis. Now you should be able to tackle the final questions in exercise 1D. They are mixed around a little bit, so you get a few requiring one method and a few requiring another method. But if you come back to these examples when you need to, you'll be able to start building a sense of which one needs to be used when, and you'll generate efficient methods for working through. Have fun.